Hello, everyone. So, in the previous lecture, we talked about the signals and systems. So, we went through some basic definitions of what are the signals, what type of the signals do we have, and then we talked about like basics in systems. We talked about the noise and disturbance, and then interconnection of subsystems. Now, in this lecture, I'm going to cover sensor technologies in autonomous vehicles. This is a very important topic in autonomous vehicles, which also has because it has an interaction with the transportation system as well, right? So the objectives of this lecture is that you will be able to uh, identify and describe the primary sensor technologies that they are used in autonomous vehicles. Like we're gonna talk about the main sensors like LiDAR, radar, cameras, ultrasonic sensors, GPS, and briefly talk about the IMU and like tachometer. So, and then you will be able to explain the operating of each sensor, some like fundamental concepts. Then you would be able to compare different sensors in terms of their range and environmental sensitivity to describe the applications of every sensor in the autonomous driving, like perception, localization, like obstacle detection and avoidance, like parking assistance, to analyze the limitations of the individual sensors. This is also an important topic to know that not every sensor can get all the information, right? So there are definitely some limitations on some sensors, some challenges due to the environment. Now, then you will get information about that, and then eventually, um, at the end of the lecture, you'll understand that why do we need to have a concept of sensor fusion, which multiple sensors they will work together and then help in the control, perception, prediction, and the performance of an AV. So, which we're gonna talk about those control sensor fusion in the next lecture. So. In AV, there are some main sensors which you can see it is a GPS, which is called Global Positioning Systems, right? So some signals they come from satellite and help in the positioning system. So for every AV, like pretty similar to what the human does for um, a simple driving. Assume that you're going to drive from location A to location B. You're going to drive from your campus to your house. You're going to go to some shopping mall, shopping center, right? So one thing which is so important is to know where you are. Okay. So like you're in the middle of the street, you want to go to right and left. Some of you like use the um, different maps in your cell phone or in your car. So that is a very important topic to know where your current location is. Even when you walk and you want to run or walk in some certain environment, so you consider that where you are planning to go, and what's happening around you. So this is exactly what an AV does. So and since the car is an autonomous vehicle, autonomous means that it's making decision based on its own perception system, all right? There's not a human directly involved in the driving procedure or helping with the positioning and everything. So this is what it requires some sensors to get to know where it is in the environment, all right? And GPS is one of them. So we're gonna talk about all these sensors in detail later in slides. So then it has LiDAR. LiDAR is a light detection and ranging. Okay, so there's a LiDAR sensor in it. It sends some lights, pulses of lights, and then detects the surroundings. So then the cars, autonomous vehicles, they have multiple camera systems, right? So you may have seen that like electric vehicles. There are so many cameras around. Again, we're gonna talk about that. So they have like so many rules like cameras used for to detect traffic lights, road signs, like keep track of the position of other vehicle, look out for pedestrians, obstacles on the road, signs and everything. Okay. So then the other sensors that we have, they are radar sensors. You can see that there is one in the back and one in front, right? Like multiple sensors on the back and front, and they monitor the position of other vehicles that they are close to the car, right? So again, we're gonna talk about that, and also the the front radar sensors. They have recently some application that we call it and some adaptive cruise control, right? So we'll talk about that in next slides. So then the AV car, other sensors that we have is ultrasonic sensor. So ultrasonic sensor is a short range sensor which is used to position like some objects that they are really close to the vehicle. Like radar, they are for like long range, like long distance objects, but ultrasonic sensors they used for a very for the objects that they are very close to the vehicle. And I teach robotics courses, and for the small robots that we design, we use the ultrasonic sensors because all those robots they're going to work in a very short range of environment. Now, so this figure is important because it shows the coverage range of the sensors, right? So you can see that some sensors like cameras, what we have in the cameras have a concept of field of view, right? So means that they can capture certain region in when in the environment that they have been installed. So you can see that like we for each camera we have surround view for each car. So we have the some cameras are installed for the surround view, some parking assistance sensors like cross traffic alert and traffic sign recognition, emergency braking, pedestrian detection, collision avoidance, and adaptive cruise control. And you can see that here. So, like the effect of using each sensor and their coverage for the car. So, cameras, they are these orange regions, that they are the coverage areas of the cameras. So, LiDAR is the green coverage, and you can see that this is the area of coverage for emergency braking, pedestrian detection, collision avoidance. And you can see that even in front of the car, there are a collaboration of multiple sensors. So you see that we have ultrasonic sensor, short and medium range radar, and long range radar. Okay, so this is where this like uh, navy blue is a short, medium range radar, and then this like cyan color is a long range radar. So And like the pink one, you can see that it's a parking assistant, is a short range ultrasonic sensor. Okay. And so these are all the sensors with their coverage in front of the car. In the back of the car, they are like park assistant, rear collision warning, like and surround view for the back of the camera. There are some blind spot detection, which like some short or medium range radar is used, and you can see that still there are some um, blind region over here, which like some other cameras will normally use to make sure that the car doesn't have any blind spot, because the issue is that if something comes from this environment, if there is any object in that region, the white region that you see between these two sensors, this camera and other sensors in this part of the car, so then the car cannot detect it. And when it cannot detect it, then there might be some collision, some accident can happen. So this is what in the back of the car, you can see that there are coverage, like this, like coverage areas of the sensor, they have overlap to make sure that at least one of the sensors will detect the the obstacle. So, and then the same thing will happen actually here as well. But this is a great actually coverage area of each sensors of an AV in its environment. Now we're gonna go over the details of what are these sensors and how do they work. So sensor technologies uh, in the AVs, the main sensors that we have there are LiDAR, we have which is high resolution. They are used for high resolution mapping, and they have a range of like 200 and 300 meter range. So we have radar, which is for detection of like speeds and distance of objects, and they are robust in like adverse weathers. We have cameras, which they are the main object of cameras are in the object and traffic sign recognition, and but they are sensitive to lighting. So ultrasonic sensors, they are short range and low cost, and mainly like in parking assistant or they which you saw over here. So and then like some as you saw here in this figure, using for objects, just avoidance of objects that they are so close to the vehicle, like such as curbs and other vehicles, like when they are pulled. So then we have positioning system. We need to sensors for positioning system. You can see that LiDAR, radar, cameras. If you take a look at here, all the sensors that we have, these are sensors for perception, for the environment, what's going on around the vehicle. Okay? So, but they are not giving information about the exact location of the system that we use. We use it through GPS and some other sensors like inertial measurement unit, like IMU. Now, let's see how does a LiDAR work. So LiDAR stands for light detection and ranging. It is an active remote sensing technology. We call it active remote sensing technology because a LiDAR, it sends laser or infrared signal to the environment. And then it captures the reflected signal from the environment and measures the distance through a concept which is called the time of flight. So and you can see that in this graph that how it sends the laser pulse and reflects that, and like there are some angles between this the like transmitter and receiver, and it is actually and we can measure the distance by considering the speed of the light and the time that it takes for the system for the signal to travel from transmitter, hit the object, and then go back to receiver. Okay, so this is how a LiDAR detects an object. So key properties of LiDAR is that it uses laser pulses to measure distance and object shapes. Like it can make a mapping. It can it creates like the LiDAR that they are used for the autonomous vehicles. They create a high resolution 3D maps of the environment and provides an accurate range, angle, and elevation information of what's going on in the environment of the robot. And it operates independently of ambient lighting. So if it is like day or night, the LiDAR still works. So applications of LiDAR in AVs, it gives 3D environment perception. So detection of vehicle, pedestrians, cyclists, and obstacles. These are some main application of LiDARs. So localization and mapping. So it gives high definition map, and we call there is a concept in the like autonomous robotics and vehicle which is called simultaneous localization and mapping. It gives some information about what's going on around the vehicle in the real time. Okay, so and it has application free space and drivable area detection, identifying like safe driving way regions, and it has object tracking, so estimating the object position and motion over time, because that kind of the localization and mapping helps with that. And since the LiDAR is working in real time, so it helps with any changes like if because especially for the transportation application, many of the objects they are dynamic, or that obstacles they are dynamic. So dynamic means that we have moving obstacles, like the human they walk through the like the road, or like if some cyclist is like having the biking through the um, the road. So then there are some moving objects. We have some moving objects, and LiDAR can detect it because it's working in real time. It can detect that. So, and it supports for motion planning. So, and it enables safe path and trajectory planning through accurate geometry. So, the LiDAR information is one of the most important information that is used for the control and perception environment. So here, so you can see that how a LiDAR works, and the this figure shows that you can see the dynamic objects, how people are moving, other cars are moving around, and and that is exactly what's going on. What car, like the control center or computer of the car, can see through the LiDAR information. And you can see this kind of the 3D mapping of objects, cars, like stores, or humans that they are walking around. And it has some certain range. You can see this certain range of front and back of the car. And that is a part, if you have seen an autonomous vehicle, like in San Francisco, like Waymo, so you can see that there's the like big circular object on the top of the car, and that is a LiDAR. So in this figure also you can see that how it actually maps the environment. So these are like there are some like trees or bushes, but it can it can detect it, and it has a 360 degree, like it moves in 360 degree and gives real time information from the environment. Okay, now limitations of LiDAR. So it has weather sensitivity. Okay, so the LiDARs, they like the weather, like rain, fog, snow, and dust, it affects the performance of the uh, laser and like attenuates the effect of laser and scatter the laser. So then it will affect the performance of the sensor. LiDARs are always like the expensive sensors in the car, especially when they are high accurate, like what we call it automotive grade LiDAR. They're much more expensive than regular sensors. So now, since it's working in 360 degree, it actually generates lots of data. Okay. Now, creating those 3D maps is not a simple work, and it requires a lot of computational resources and memory resources, which affects the control, right? So that is also important to consider that. And LiDAR, even though it makes the mapping of the environment, it doesn't measure directly the speed of the objects that they are around the car. And there are some surfaces that like that they absorb or scatter the laser lights, right? So like black surfaces like rubber, dark clothing, and rough surfaces that they absorb the laser, which is an infrared signal, and affect the reflectivity of the signal. Those affect the range of performance of LiDAR. Now, another issue with the LiDAR is that it's spinning all the time. Now, that spinning, it affects the performance of the LiDAR because it's a mechanical actually like it has a mechanical part which is moving all as long as the vehicle works. So it can be all day. And those moving parts, since they are mechanical parts involved, it during the time, those will actually have some sort of the durability and reliability of the parts will reduce over the time. So this is what after every couple of based on how the vehicle works after a certain amount of time, so those LiDARs needs to be replaced. And you can see that they are, and you know that they are very uh, high cost sensor. Now, the other sensor that you use in AV is radar. So radar stands for radio detection and ranging. It is also an active sensing technology that instead of laser, because laser is a signal, an infrared signal, and radar uses radio waves signals to detect object and measure their range, and even it can measure velocity and angle. So the distance between the like receiver and transmitter, like when the sensor sends an information, it goes to the object, and then the reflection of that signal comes to the radar. So the distance is estimated from the signal time delay. So how long does it take to go and then receive back? And velocity is obtained via a concept that we call it Doppler effect. So this sensor is widely used in automotive systems because it's so robust and reliable. Key characteristics of radar, if you want to talk about that, is it's highly robust to adverse weather. Like, you know, the laser, it gets affected by rain, fog, snow, but radar, because it's a radio wave signal, it is highly robust to adverse weather. And I want you to think about that. So you can see that the combination of these signals, so one of them has some like advantage, the other one has some limitations, they will cover each other. So it can directly measure the relative speed, all right? So relative speed, I mean that relative speed with respect to vehicle, right? So what is the speed of like a pedestrian or other car with respect to the autonomous vehicle, which is critical for collision avoidance. Like if like some uh, car is getting close or have certain like going to coming to certain range, then the car needs to do some action. So it has longer sensing range compared to LiDAR for some certain configurations because of that using the radio wave frequency. It has lower resolution than LiDAR or cameras. Like this means that so you don't have a lot of computational, you don't need a lot of computational resources or memory to use that. So application of radar in AVs, we have it as object detection and tracking. They help that obstacles and like when there are some objects in at short or uh, long ranges, they can detect that. So they help in adaptive cruise control, right? So adaptive cruise control. Um, I don't know if you have used it or not. So when you use a cruise control, so it actually takes your speed on the certain speed, and then once you press the brake, so then your cruise control, the normal cruise control will actually disconnect, and you need to set the speed again, and then have it working. But the adaptive cruise control is where it will automatically reduce the speed when car gets closer to some like other cars when you use that in a road. And then once the object like you pass the car, it will automatically increase the speed to the speed that was initially set as a desired speed for that. So this is what it's called adaptive. Like it reduces the speed and then increases that. So then the collision avoidance systems is where it helps with that, the forward collision warning and automatic emergency braking. So it helps with, and that is a part of the control system, right? Which this kind of the sensor information goes to the collision avoidance systems to make sure that it will generate some warning or it will generate some automatic emergency braking. So it is an information which is used for sensor fusion, and it complements LiDAR and cameras to improve reliability of the of the AV in all conditions. So limitations of radar um, goes to the the limited spatial resolution because it works on only certain environment. Even you saw that in the coverage is limited. So while the uh, LiDAR can have the more wide area, so it has like the limitation in object classification, so it cannot distinguish the type of the object, if it is a pedestrian, if it is a cyclist. So we cannot detect that without sensor fusion. Multipass reflections, so the signals can reflect of the building, guardrails, and large vehicle, um, and cause false detection in the radars. So there are some angular accuracy limitations, so which reduces the precision in lateral position estimation, especially at long ranges, and it has reduced performance for non-metallic objects like such as plastic, rubber, glass, wood, vegetation, and some objects like that. Now, the next sensor that we have, which is a very useful sensor in AVs, is camera. We have three kind of the cameras. We have 2D, 3D, and thermal cameras. So cameras are passive optical sensors that capture images of the environment using visible and or infrared light. So 2D cameras, they capture uh, you have used the camera like in your cell phone, or you have a camera for taking picture. So the camera, it captures intensity or color information of the scene projected on a two-dimensional image plane. So they provide um, rich visual and semantic information like color, texture, and shape, but do not, like 2D cameras, they do not directly measure depths, right? So depths will be actually measured by other, um, like certain approaches can be used to measure through the 2D cameras or through the stereo vision, right? So some surrounding view cameras are like the cameras that they are around the cars. They are 2D cameras. So 3D cameras. So the issue of the 2D cameras is that they do not measure depth, but 3D cameras, they capture both visual information and depth information for each pixel in the scene. All right, they will give you like some RGB, like some image of the environment. Then they will give you that each pixel has what distance through the camera, right? So then you actually have a depth map or point cloud. So to directly measure the geometry of the object. So it's the depth feature uh, of a 3D camera, like stereo vision, is measured through the time structured light or time of flight, or we call it like TOF. So there are so many, like these kind of the cameras are used again for object detection and other other features in an AV. So we'll talk about those advantage of that. So then there are thermal cameras. So they detect infrared radiation emitted by objects based on their temperature rather than reflected visible lights. So this is what it's a thermal camera. So imager they produce images, that those images, they are representing the heat signatures. Um, and that is so important because it's independent of ambient lighting. So no matter what is the lighting feature in the environment, so then the camera can capture the heating signature of the object. So, and the great application of thermal cameras are in low light or nighttime conditions, right? Which, you know, uh, affects the visibility of the regular camera. And it's highly effective at detecting warm objects like pedestrian, animals, and performance is less affected by shadows or glare than visible light cameras that they have that. So application of thermal cameras is in a nighttime pedestrian animal detection, safety enhancement in low visibility condition, and it's a complementary sensing for camera, radar, and LiDAR fusion. So key characteristics of cameras are in high semantic resolution. So it's excellent for recognizing color, text, and object appearances. So why is it important? Because you know that when when we have the autonomous vehicles, so and they are on the road, so detection, object detection is important, but the some main part of the AV is to make sure that they can read signs of a road carefully, right? They can see that and observe those signs like a stop sign, like any other like traffic sign, and the color in the traffic sign is not just an object like LiDAR and radar. They just detect those uh, as an object, as an obstacle, but they don't know anything about the shape, about the color, about the the object appearance. Okay, so that is what the cameras are so important in that region. So they are low cost and power uh, consumption is much lower than LiDAR and radar. So it's a flexible placement. You can put it like front, rear, side, and so on. And even you can see that they are almost everywhere in the an autonomous vehicle, and even in the regular cars you saw them. And their performance depends strongly on lighting and visibility conditions, which is actually a drawback. We're going to talk about that in the limitations. So So applications of cameras in autonomous vehicles. So it's in object classification. So identifying vehicles, pedestrians, cyclists, and animals. Traffic signal and sign recognition. That is the main part. So it can read lights, signs, and road markings, help in reading this kind of the features of a transportation system. That's another important feature or application of cameras. So lane detection and tracking. So you know that like radar and LiDAR, they are mainly working on those mapping, localization, mapping, and detection, object detection, and the like relative speed of an object with respect to the car. But lane detection and tracking is a main feature of the camera to support lane keeping and centering in the lane. So scene understanding, so you have an understanding of the semantic segmentation of the driving environment. So with the area that the AV is working, and driver monitoring. So there is a concept of advanced driver assistance systems that helps in monitoring driver attention and behavior. This is what the cameras help with that ADAS. So, and like other sensors, so you saw that all the sensors that we talked about it so far, they have some key characteristics, they have certain applications in AVs, and they have limitations, right? So the cameras also the same. So they are sensitive to lighting conditions like night, glare, shadows. They affect the performance um, of the cameras. So performance of the camera, they degrades in rain, fog, and snow. And there is no direct depth or velocity measurement if you don't have if there is no like a stereo. Like definitely if there are the stereo, they can measure the depth. But normally the sensor fusion is used like using the different sensors in order to do the velocity measurement. And so like occlusion and visual clutter, they can reduce the reliability of the camera. So I have multiple images here to show that how the some like environment, some effect in environment in different areas and in different conditions can affect the performance of the cameras, all right? So here you can see that they are that some dirt or like some leaves over here that can affect the lane detection, right? So here the snow covered the lane markers, right? So it's gonna be difficult, and one of the objects, one of the applications of the cameras is lane detection. Or so here you can see that um, top of the concrete. If you take a look at it over here, so they look like a lane marker, right? So then that also is something that uh, camera may by mistake detect that as a lane marker. Or lighting, right? So here, this is like some image at light, here like effect of lighting in like early morning, and you can see how that lighting can affect the performance of the um, camera and also resolution. Like if the quality of the camera is not good, you can see that the picture that you can get and you can watch from the camera doesn't have the good quality to be used for an AV car, autonomous vehicle. So, and again, lighting is another issue, whether like if it is fog or if there are so many lights, that these are something that they also affect the performance of the camera. Now, another important limitations of the cameras is where, so there are um, like so many signs, okay? And the car has the normally like assume that here this is a highway, and the car has a high speed, and it's going to detect so many objects, right? That also affects the performance and needs a lot of computational resources to make sure that it can pick the correct time. Now, so we talked about LiDAR, we talked about radar, we talked about the cameras. Another sensor that is used in the AV is ultrasonic sensor. So it measured distance using like sound wave, but high frequency sound wave, and the sensor like pretty similar to radar emits a pulse and measures time of flight of return, and distance is calculated using the speed of sound and return time. So for the laser, which we have for the LiDAR, we have the speed of light because that's a the laser is an infrared signal. So, but here we have we have the sound wave. So we have the speed of sound and return time, and we calculate that. It's much it's much simple, like development, even working with the ultrasonic sensor. It's so simple and it has a lower cost. It's much cheaper than other sensors. So now, ultrasonic sensor is a short range sensor, like between zero point 0.2 meter to 5 meter. So, like it has moderate update rate with minimal processing. It doesn't require it doesn't generate lots of data, and it doesn't require complex and heavy computational resources. Um, Now, if the range is too close, it has a good resolution for that. It doesn't have the complexity again compared to other sensors. So, parking assistance, some applications of ultrasonic sensors, like some parking things are measuring the boundaries in parking, blind spot detection, like if there are some other vehicle that they are in the blind side at some tighter distances. Collision detection, like alerting to obstacles in the way. Pedestrian detection, like some safety. Again, these are complementary. All these sensors they are complement each other. So limitations definitely for the ultrasonic. It's a short range. It has poor performance at higher speed when the speed like in freeways or highways when the speed becomes higher, like the performance reduces. And even it's not at that speed. We don't have like that kind of the close vehicles. Like it may not happen. Uh, and it cannot classify object, it just detect, all right? Uh, and it just measures the distance. And it also gets affected by temperature, noises, and some angled surfaces. And you can see over here, if you have like obstacle have some angles. So it actually sends a trigger signal and then it will receive it. It will wait until it receives the signal. But if you have some angled obstacle, then it may not even receive that. Now, all those sensors, they are mainly affecting the environment of an AV, right? What's going on in terms of the mapping of the environment, what's going on in terms of the, um, you know, collision detection, in terms of detecting some signs, detecting like road lane and everything, like lane signs and everything. Now, in order to know where the car is, where the AV is, we need some positioning systems, right? So the main positioning system that is used for the vehicles in US is GPS or Global Positioning Systems. Uh, so those positioning systems, the data packages they sent from a network of satellites. It's a network of satellites that they gather information from the object and then send it to some receiver. And that receivers are the GPS receiver that is installed in the car. Okay. So, and data includes the geographical data, includes latitude, longitude, altitude, and speed of the vehicle. It provides other information as well, but these are the main data which is used for the positioning of a vehicle. So it depends. Like GPS has different kind of the accuracy, but like between 3 to 5 meters, like there are low quality and they are high quality and like more accurate. That definitely it increases the cost of the GPS receiver sensors. So there is an update rate between 1 hertz to 10 hertz. It has a global coverage with network of satellites and it like operates independently from other systems, like other sensors. Because the the receiver, all the information comes from the satellite, so they operate independently. Um, and again, they're not connected to any internet or Wi-Fi connection. They don't need that. So they help with the global vehicle localization, where the car is. So route planning and navigation, like what is happening in the map in your car, that there is a start point, there is an end point, these are the locations on the geographical environment. So then it can plan the route, and velocity approximation can be used to calculate the speed uh, from the start and end. And network of GPS data help with multiple like AVs. So limitations of GPS include signal blockage, like dense trees, tunnel block, and tunnels. They block the satellites from reaching the receiver. Like receiver cannot receive information, then you will lose the GPS information. I know that it may happen. You may have had that when like you travel to certain area. It's not reliable for lane to lane level, so it cannot tell that which lane AV is, right? Maybe in the future when there are like some intelligent transportation system, they might be able this can be used for that, but currently it doesn't have anything. So and it doesn't prevent collision with GPS alone. So it just gives you the location. It doesn't tell anything about what's going on around the vehicle. So those other um, like information comes from other sensors. So now GPS has a limitation, and positioning of an AV vehicle, of an autonomous vehicle, is a critical feature, right? So this is what other sensors than GPS is used in an AV for to help with the positioning. We call them, they are some supporting sensors for vehicle positionings. So they are include inertial measurement unit, like, or we call them IMU. It includes an accelerometer and gyroscopes, and measures vehicle acceleration and rotation. It provides short-term position and orientation estimates, and it's especially useful when GPS is unavailable or unreliable, right? Like in tunnels, like urban canyons. So it can give some estimation of where the vehicle is when GPS data is unavailable. So another sensor is tachometer and wheel speed sensors. So they measure wheel rotation speed, and it used to estimate vehicle speed and travel distance. Like, because once you have the um, like the speed of the wheel, so you can measure what are the distances traveled, and it enables autometry based positioning and helps with bridge the gaps during the GPS dropout. Uh, so again, GPS alone is not always reliable. So then IMU, wheel speed sensor, they provide continuous motion information, which combined with GPS through sensor fusion, which we're gonna talk about that, they actually improve accuracy, robustness, and reliability of vehicle positioning. And that is what if you take a look at all the slides that we covered, all the sensor information that we covered together, you can see that um, for an AV, autonomous vehicle, these sensors they all need to work together to make sure that the vehicle at the end will have a safe and reliable um, actually performance. So that is what for positioning system we have their own system. For other like environment, like detection of what's going on around the vehicle, we also have that radar, LiDAR, and other sensors. So this is what in the next lecture I'm going to talk about the sensor fusion. So these are some techniques that this sensor information they are um, actually um, they are used, some techniques are using this sensor information to um, provide some information to the control and perception and planning and make sure that the vehicle will work properly in different environment. Considering that some sensors doesn't work, like in terms of when the weather changes or when the lighting changes, or if it is a night, if it is a day, no matter of what the area, if it's like heavy snow, the temperature is too low, too high, the vehicle will keep functioning. And these are some references for that if you are interested to look at this further. And this is all for this lecture, and have a good day, everyone.